Hello, everyone. It's time to start our meetup. So, welcome to Yandex Armenia AI Meetup. My name is Ikas Muradyan. I'm working at Yandex Telemost. It's totally not related to AI, at least except for text recognition. But I'm your host today. So let me now learn who is gathered here. Raise your hand, please, who knows Armenian. Okay. English. Okay. Russian. Okay, so there will be no worries that someone didn't understand something. Okay, and also raise your hands who studied at Yerevan State University or former student or something. Yeah? Okay, that's great. So we will have several sections today. We will have welcome speech from Aram and Karen. Then we will have our speakers. Then we will have panel discussion, and then time for coffee time and learning each other better. The speakers will not have many time to talk, so it will be like 50 minutes per each. So if you have any questions, please ask them later after the talk, so we will not have time for the questions after the talk. So you can catch them during the coffee break and ask your questions there. Okay, so welcome Aram Khitaryan, head of Yandex Armenia. He will give his welcome speech and describe what will happen next.
More of this. Good afternoon, everyone. So I will continue in English. So my name is Aram Khitaryan. I'm the regional head of Yandex in Central Asia and Caucasus, but parallelly serving also as a head of Yandex Armenia and Georgia. So you are now in Yandex Hall. This is the place that we have designed as a center of gravity for IT community of Armenia. And today's meetup and also the contents fully aligned to our mission. We are trying to create an atmosphere, create an IT community center here in Yandex Hall to provide the possibility to our community to meet, to learn, to discuss, and to build something new together. So I'm really welcome all of you today here. So at Yandex, and me myself as an engineer, I'm pretty sure that the main thing that it's really important, it's a fundamental and background for the engineers. Because all of technologies, I don't know, frameworks, languages, they will be changed, but mathematical background, algorithmic thinking, and problem-solving skills, they have value for lifetime. So let me welcome you. I will be short. So let's start.
And now I want to give word to Karen. Karen is head of applied statistics and data research at Yerevan State University. He will say a few words as well.
I'm Karen Keryan. I'm co-head of applied statistics and data science program at Yerevan State University. So there are kind of two things that all of us are gathered together here. For one reason is the contest, and the other reason is AI. So both are kind of at heart for me. So we have been organizing Math Olympiads for 15 years at Yerevan State University, and basically we are going to have yet another one next Saturday. So if you are interested, you are very welcome. And on the other hand, our master program in applied statistics and data science. So here we also see a lot of interest and the number of students that are applying to our program is growing year by year. So last year we had more than 80 applicants, and we have selected 35. So actually, among the winners, we have one of our students, current graduates, and so if you want to have a nice synergy of theoretical and applied part of AI, so by coming to our master program, you can see both. So the theoretical part is covered by academic experts, and the theoretical part is covered by industry professionals, team leaders of Pixar, Crisp, and many other companies in Armenia. So we can just talk during the coffee break that we are going to have. If you have any questions, please feel free to ask, and you can have some more information about our master program at asds.ysu.am. So thank you very much, Yandex, for organizing this meetup, and that is yet another nice opportunity to gather people interested in AI. Thank you.
Okay, so now the word about our speakers who will speak today. So first will be Dmitry Duka. He is Director of Technology at NVIDIA. He will talk about AI research. Then we also have Sergey Kolyubin, who is Deputy Head of School of Computer Technologies and Control at ITMO University, or ITMO, I'm not sure about this. Then we will have Bulat Huseinov, who is Team Lead of Data Science in Yandex AliceAI. And then we will have panel discussion, which I will talk about later. So our first speaker will be Dmitry. He, sorry for that. He is one of the main persons at NVIDIA, as I understand. So he will give us talk about the research. Welcome, Dmitry.
Thank you for inviting me here. Yeah, a little bit about myself. I joined NVIDIA in 2010, back in Moscow. We moved here then, and now I'm the Director of Technology and also the site lead for NVIDIA Armenia office. My background mostly is systems and GPU programming, so give me some slack. I'm not an AI expert myself. However, I will attempt to talk a little about physical AI. Thank you. And what NVIDIA is doing about this. Okay, so training a robot or autonomous car is really hard, mainly for the reason that this is a real system, and in order to be trained well, it needs to receive the feedback from the real world, and it takes a lot of money and time to get this feedback, to basically get a good train set. I think this is the number one reason for why the physical AI is stuck, essentially, compared to all other types of AI, right? Like LLMs and generative models, we have them. They're fairly good already. They will be even better, but with physical AI, we don't have as many cases where it's it's right here in your face, right? And so the way NVIDIA approaches this problem is through simulation. And we've presented at CES in the beginning of this year, I believe, the technology called NVIDIA Cosmos, which is a whole platform, a collection of models that allow you to generate realistic videos for robots. Right, so what you're seeing right now is not a real video. And the way we do this is we approach this from like different angles, right? So Cosmos consists of Cosmos Predict, which is a video generative model capable of generating, I believe, up to 30 or 60 second long videos based on a multi-modal input. We have Cosmos Transfer, which is the one that I'm probably going to focus a little more on today. We have Cosmos Reason, which is what's... I'm going to also talk a little about Cosmos Reason and how it's used. And then we have CDS, which is Cosmos Search, for searching within big data sets. And all of these pieces really work together. And with simulation, we of course couple it with NVIDIA Omniverse, and that's where I work, the simulation part of NVIDIA. And the approach we take with, say, Cosmos Transfer is we can simulate certain situations. We can set up, say, for a robot, we can set up the environment that is as accurate as possible, especially physically speaking, as accurate as possible. And the benefit of this approach, of course, is that we can get all the annotations essentially for free because the scene is artificial, right? And then, of course, we have all this nice photorealistic rendering with ray tracing and whatnot. However, there is this gap between the what we call sim to real gap, right? No matter how realistic the scene is, even though with ray tracing we're capable of producing very nice images and videos, there is another problem, which is the problem of authoring, right? What I mean here is if you just want to render, say, a cube in an empty room, in an ideal empty room with one single light source, we are easily able to render this scene in such a way that it's not going to be distinguishable from a real photo taken in the same environment. However, normally such environments do not exist. There's a lot of, like, I don't know, dust, randomly scattered, leaves, all these minutiae of real world, and it's simply too hard to even reproduce it like we've used to do this with, say, in game industry, where you try to recreate a scene with just 3D models. And so this is where Cosmos Transfer comes in, where it can add or change the scene according to the prompt. And so basically what happens is you produce this scene and you take the most value out of it by taking all these maps, right? Like instance bounding boxes, depth map, which is obviously as precise as way more precise than you could take with a real-world depth camera. All the texture information, material, etc. And then you feed it all into the Cosmos Transfer plus some prompt, and it produces a realistic video that can then be used for training the robot, right? Yeah, so it's this like semantic segmentation, instance segmentation, depth maps, all these maps are playing an important role for as a one of the possible inputs to the Cosmos Transfer. The nice side effect of this, or just another benefit really, is that with this approach we can easily cover edge cases which rarely happen in real world, or it's just hard to produce such a real environment where this edge case might happen, right? The good example would be a car where you would for example, like to have a sample in your data set that has a tree falling right as you drive, right? But it's a fairly rare occurrence, and so it's going to be a problem for you. But with simulation, of course, you can produce with just a bunch of prompts such a data set and check how your car will react with in this environment. Of course, Cosmos Transfer can also be used to do video-to-video changes, right? So you don't have to first produce the simulated scene in Omniverse and all these different maps that I talked about. You just can take a real video plus some prompt and produce a different lighting. The good example would be if you, say, train a self-driving car and you would like to change the time of the year, right? Add some snow. Easy, you can just put video, prompt, and produce another video. One thing that I was talking about is Cosmos Reason. One other thing that I was talking about is Cosmos Reason, which is a fairly small model. I believe it's 7 billion parameters that is used in NVIDIA Alpamayo, which was also announced in the beginning of this year. And it's basically reasoning added to the VLA model that is used for self-driving, right? So we've all seen how big an impact was the reasoning, the addition of reasoning for LLMs. And this is the same GPT moment, I would say, for self-driving, where the car is not only producing actions as an effect of inference of what it sees, but it also has this reasoning portion in the middle, which tries to explain what it sees, essentially, right? And so in these edge cases that I was talking about, you can really improve the quality of self-driving experience because the model is basically able to, well, reason about what it sees, like, for example, oh, the tree is about to fall, or this rock is about to roll on the road, I must stop. And so this kind of out-of-sample examples are covered much better with Alpamayo. And the idea, of course, is that it would be inferenced right on the car with hardware that basically, yeah, the piece of hardware is obviously not like B200, B300. It's way less performant, but it's enough to run this model. And finally, the other example where the same approach is used in Cosmos, really all parts of Cosmos are used in Transfer and NVIDIA Omniverse, and Cosmos Reasoning is for Isaac GR00T, which is the platform to train humanoid robots, right? The idea there is exactly the same, where the robot can reason about what it sees and decide on the fly what should happen next. I think that's my last slide. That's all I wanted to talk about today. Thank you.
Actually, since we ran a little bit earlier in our time, we have like several minutes for questions, but if you don't have them or you didn't prepare them, you still can have them later. So, or maybe we have something with question right now. Okay, no, you didn't wake up yet, that's okay. So, before we proceed with our next speaker, I want to ask several questions to you. About using AI in your common life, like in your personal life, in your study, in your work, like to figure out how deep you are in your AI usage. So raise your hand if you use AI for work or study, like very often. Okay, so like half of the people. And how often do you use AI in your personal life, like for your personal goals, when you want to figure out something, and or maybe use it like a psychologist or something? Okay, okay, that's good. And like how often you use AI for your creativity or trying to create things, like when you totally don't know what to do? Okay, okay, that's very interesting. Thank you. Okay, so our next guest is Sergey Kolubin. His section is about from words to worlds, speaking physics, native intelligence. He is professor and vice director in School of Computer Technologies and Control at ITMO University, or ITMO. What is correct? ITMO or ITMO? ITMO. Okay, okay. So please welcome Sergey.
Okay, thanks. Hello, everyone. Or Baravzes, right? So, first of all, I would like to thank organizers for giving me a great challenge. I have like 15 minutes to give you my perspective on the entire brave new world, right? So, and also we're in quite a real situation. So imagine that you heard something from the news or from, some big tech company, and now you invite a professor who should somehow systematically build up an intuition behind that, okay? So let me try to do that. And first of all, a few words about myself. So I wear multiple hats, but the one I like most is being a professor in robotics at ITMO University and also heading the beer lab. Has nothing to do with beer, right? But that's just biomechatronics, energy efficient robotics lab. So this is at least how it was called from the very beginning. But actually, we started our journey almost like 10 years ago, and from the very beginning, we've been focused on embodied intelligence. So we focused on that much in advance before it became like a hype word, right? For now, you hear about embodied intelligence from almost everywhere. So, and we emphasize two specific aspects, in particular robustness and energy efficiency, as essential aspects of scaling solutions that we develop. Because if you develop something that is fragile or not efficient, and we see that nowadays, right? So we run out of energy. We ban building new data centers and doing something like that just because we run out of energy. So yeah, and for now we grow up. We are more than 30 people, and we contribute a lot to open source as well. So, and if you like, you can follow the links that I provide over here. Maybe you will find something interesting for yourself as well. Great. So, as a disclaimer, I will say nothing about NVIDIA stuff over here, not because I don't see or don't value that. That's amazing things. Just because you already had a speaker, and that was a very nice advertisement on the, that's amazing stuff that they're doing. Okay, but to help you build intuition, I will use some primitives, okay? We'll talk about vectors, cycles, and spirals, okay? So, and the funny thing is that if you combine the first two, you get the last one, okay? So let's start from vectors. Where vector is going from and to. Okay. The large models era started from language models. You can ask why. So the answer is, yeah, we had a lot of cheap fuel all around in a digital form. That's natural language. So basically, the way we transferred knowledge from generation to generation. Most of that is actually garbage. That's not good. But that was good enough to train something big. And while we've been working on that, we just figured out that the architectures, methods, and pipelines we created are scaling to different modalities. So, and therefore, we created large multimodal models, which can work with visual data, voice data, etc. And this way, we created LMMs. Nice. So, but frontier for now is large behavioral models. That's a model that help an agent, let's call it like a physical agent, to actually perceive the world, understand that, think about it, plan actions, execute, and interact. So, and I believe that the next big thing is not just a better chatbot. That is something that can really act. So even ChatGPT can't finish any building now. General purpose robot, GPR, will. Okay, that's my belief. And I will try to convince you as well. So, and since we'll be talking about AI in different aspects, let's put some dots above I. Okay? So now you hear physical intelligence, physical AI, embodied AI, and people almost do not distinguish between that, right? So, but let me give you a bit of understanding from my perspective. So, and first of all, not any AI that works for physical processes can be called physical AI. Physical AI is like a paradigm to make AI understand physical world, understand its principles, right? Okay. On the other hand, there are many applications, useful applications of physical AI that are disembodied. For now, we use physical AI to predict weather, for example, or forest fires, or I don't know, build molecules, or do other stuff that runs on huge clusters and not in real time and has no body. That's disembodied. Okay. On the other hand, there is embodied intelligence. That's a much bigger field. It's not only AI. So we'll talk about something as an intersection between physical AI and embodied intelligence. We'll talk about embodied AI. That's like bringing physical AI to bodies and also putting extra constraints that it should work in real time and on the edge, right? So this edge compute, something small. So what is so special about embodied intelligence? Because we know a lot of things from control systems, from system theory, so robots exist for many years, right? So what is so special? So last year there was a report from AAAI, that's American Association of AI, on the frontiers of AI in general, right? So, and one of the frontiers, one of the key frontiers, they call like embodied AI. So, and they say that for embodied, there are 6 E's, right? So that's over here, like embodied, embedded, and active, blah, 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 right? In my opinion, the game changer is that it's actually evolving, so the system can improve over time through active interaction with the environment and even discover new emerging capabilities. That's something that didn't exist before, and that is something that is really changing the entire automation robotics game. Okay, so can we have all these, capabilities using the same approaches we use now? So according to Einstein, that's not the best way probably, right? So, and the current ML is mostly statistical learning. And from statistics, from numbers, you see something good. It's converging, the covariance is good, correlations are nice, etc., etc. But from the actual, from the physical perspective, that's just nonsense, right? Mass cannot be negative. Energy cannot be negative, something like that, okay? So that's also greedy for data, greedy for compute, and that's fragile, right? So statistical approximations, we all know about overfitting. Right? You have nice convergence curves, everything is fine, you deploy it in the real world, you have sim to real gap, and then it breaks. That's very fragile. So what is the new wave? The new wave is, in my opinion as well, is contextual adaptation. The system can adapt to context or take context into account. And here I distinguish between 2 types of the context. The first one is global. That's physics. That's laws of nature. That's something that you can't break, you cannot ignore. Okay? So, and then there is a local context. The local one is basically understanding what is going on right here, right now. That means semantics. So understanding the meaning. Therefore, I'm not talking about, sensing. I talk about perception. And that's very different. Good. So that's about the vector. So you see where the vector is going from and to. So now let's talk about the cycle. And when we talk about agents, embodiments, embodied AI, we have a sense, think, act, interact cycle, and since it should evolve, that's like a closed loop. Okay, Good. To have this cycle running, we need several key enablers. There are different aspects of that. There is like a cognitive layer and also a physical layer. So for today, we'll focus on the cognitive layer and two key enablers for the cognitive layer of embodied AI, which are data and training. So we need, in terms of data, we need some dense, information-rich, non-contradicting representations building up in, let's say, robot brains regarding what it perceives, right? And that's not natural language, because natural language is ambiguous, at the same time it's contradictory, is not complete, etc., etc. So natural language is probably not the best. Therefore, for now, we see like all these joint embeddings, prediction architectures, right? So did you hear about that? Yeah, great. At least one hand, that's great. So that's like building some latent, specific representations that's not even human interpretable. And let me put it this way, at some point, human is a bottleneck at this point. So, and the other aspect is training. We need some architectures and methods that allow models to be trained in a sample efficient way, so from when you have just few shots of the data, or zero-shot training. And you need something that can generalize as well. That's very important. Okay, so let's start from the data. And we're turning to the age of hard-digging fuel for AI. Right? So we run out of natural language. We run out of all these cheap resources that we had before. So now we have to work with direct sensory experience of physical agents. Right? So it's not just language. And that's not so easy to provide availability, applicability, and scaling of raw sensory data. Scaling in terms of how fast we can get new data as well. That's very important, and you need to scale in training. So we need cheap and fast rollouts, and there are two ways. At least these are the two ways that research community is, exploring right now. The first one is to crowdsource data. Right? So you have, instead of books, you have video archives. Unlabeled, unstructured, uncalibrated video archives. And you need to turn that, let's say, silicon into diamonds, right? You need to somehow condense and, augment that one. The other way is generating synthetic data. And Dmitry already talked about world models and, these virtual worlds. That's great. The challenge over there is that making that physically consistent, right? So that your world model is actually, reproducing the world we are living in, not some, imaginable one. That's very important. So now a bit of, advertisement on the works that we've done for the last couple of years in my lab and addressing these particular challenges. So the first one is gsplotlock. That gives you, so I will not have time to explain in details, just to give you a glimpse of what is going on over there. And for now, there is a powerful technique to build representation of the environment using Gaussian splitting. That's like 3D Gaussians. So it's a quite powerful technique that's also quite physical because Gaussian is like a particle, right? And you can parameterize that, so that's called direct DNN-based representation. So, and we implemented something like that to build up 3D reconstructions of the environments. Also dynamic environments, which is important. If I want to build like a map of what is going on over here and we have all of you, should I add you there or should I somehow mask all the dynamic objects to have like a representation that can live or be actual for a longer time? And then how to localize within the environment. Not like traditional techniques do from like visual features, but from descriptors and descriptors applied to Gaussians, etc., etc. Good. So if you're interested, you can discover also the links. Maybe slides will be shared as well, so you can understand better in the details. Another stuff is synthetic data. So we create, and also that's important to have a proper benchmarking of what you develop. So we developed a so-called Osmo bench. So this is a benchmarking approach, which is dynamically creating situations that are challenging spatial intelligence pipelines on the go. And we use synthetic data for now. So at first we used habitat sim, now we use SynSmith. So basically you can generate corner cases from prompts. Shuffle objects, change illumination, do the stuff, and see how actually, how from different visual inputs your model performs. If it's stable, if it's not, how robust is that, how generalizable is that, etc., etc. And everything is going just automatically, right? Good. So, and quite a recent work that we released is focusing on the one hand on SLAM, simultaneous localization and mapping. On the other hand, that's actually one of the ways to crowdsource data or to turn crowdsourced data into something useful for training. So there are very hot directions in robotics for now in particular. The one is called agglomerative model. Probably heard about CLEEP, CGLEEP, Dino, all these kind of encoders. So for now, there are attempts to distill all capabilities into a single model, take the best of all these worlds. So, and radio is the model that is developed specifically to distill. So that's called, radio is actually an abbreviation for reduce all dimensionalities into one, okay? And there is another hot topic, which is like a continuation of 3R pipelines. 3R is like duster, master, all these kind of pipelines. That's when you just have raw data, monocular, you don't have any depth perception, but you build 3D reconstructions out of this raw monocular data. And you don't have any parameters of the cameras, etc., etc. These parameters are estimated on the go as well. So we combined that, optimized, had some tricky things like robust kernels and optimization, and we released Radio Vibe that can be also used to process raw data, augment, have something close to ground truth, poses of the cameras, of objects, masks, etc., etc. So, and that's works in open vocabulary, which means that's not closed set of objects. That's almost any object. Okay, can be recognized, masked, etc., and then used for grounding. So that's about data. So another story is training and architectures that are generalizable and sample efficient. And here we should talk about physical consistency. What does it mean being physical consistent? So for now, training is like a search process. Basically, you do search, but you search a huge space, right? You need to discover that. You need to find some optimal solutions within this search space, right? So to make it faster, you need some guardrails. And for physical world, we do have guardrails. These are physical laws that we all discovered. Euler-Lagrange approach, Newton laws, all that stuff, right? That's our guardrails. Sure, we should use that, we should implement that, and there are different ways to implement that. That's called bias, okay? And we have different kind of biases to provide physical consistency. One is called observation biases, when we augment data in a proper way. The other one is called inductive biases, when we build a specific architecture that implements these guardrails within the training process, within the architecture of the neural network. And finally, that's a learning bias. And learning bias is basically how we define, how we design our loss functions, okay? So there is also another work from my lab that will be presented also at ICRA this year. That's called U-Window. So we did some stuff for challenging environment and so on, resilient autonomy for underwater. So you have an underwater robot and you need to localize that just from visual, monocular visual, IMU, that's cheap IMU sensor, and nothing else. And underwater, there are not many visual factors, to use as features to localize. So therefore, we augment that with dynamic model, right? And dynamic model is not only first principle model. So underwater, that's hydro law, that basically is initially you should write Navier-Stokes equation and SPDE equation. That's quite hard, to describe everything and define these parameters like friction with underwater, etc., etc. So therefore we said, okay, let's build up a deep neural network and train it in a way that it respects physics, right? And we use so-called Port-Hamiltonian neural ordinary differential equations, the PH node. So we use that, and therefore we can fuse raw sensory data with our predictions on a longer horizon, which are robust, etc., etc. Good. And now, that's about the cycle. And now let's talk about the spiral. So the spiral of intelligence evolution. So I work in the domain of control science for almost 20 years. So, and when I was trained as a control engineer, we had these block representations, like subsystems. You have like a model, you have a planner, you have a controller, blah, 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 blah. Everything in blocks. Then we said, okay, that's not so powerful. That's like, old-fashioned stuff. Let's do end-to-end. Let's do monolithic models. Let's have like actions directly from sensory data. Great. So, and there was a phase 2, end-to-end learning. But when we moved on with interpretable and reliable systems, it turns out that it's not good enough. And we need to find, basically go back to these block structures, but on the new basis, on DNN basis. So for now, we're working using so-called composite architectures. And for these composite architectures, we can combine things in different ways. So we can have like dual systems, one system and another system complementing each other. We can have agentic pipelines, so they self-organize, they specialize on different functions, etc., and we can have mixture of experts, and probably heard about mixture of experts within the LLM context, right? So there are mixture of experts within embodied AI as well. Good. So this is also work from my group that's on visual tactile language model. So I believe that to train pipelines that can scale to physical interaction with the world is not like pick and place, but something that you need to assemble, insert, fold, etc. You need to complement visual modality with tactile as well. So therefore we create this one. And this is an example of dual system as well. In a way, we have fast system and slow system, right? The slow system is VLA based plus tactile. That's just working like 10 Hertz frequency. That's not fast, but it's mostly reasoning, right? And then there is a fast system that provides like fast real-time control loop. So these are some examples of the skills that we can do, so it's like sorting and door opening, etc. So we reached like 90% above success rate, and we also did some tricks to actually speed up collecting the training data. So still learning from demonstration, just 3 times faster, okay? So, and these are the works not from my lab, but these are works that are known all around. So, as I said, I will not mention anything from NVIDIA, just because you had like a special talk on that. But the one is called Maestro. Maestro is an example of like when you have an LLM that creates a code to be executed. That's also like an example of, dual system, right? Or agentic system, let's put it this way, right? So you have like an agentic system. And there are agents that do one thing, the other thing, etc. At the end of the day, you have the code that is executed in real time on the robot using the traditional control system of the robot. And it's zero shot, right? So basically, you don't need extra data. You just train something, you train a programmer. You train something that can just write code. Good, so. Another example is for mixture of experts. It's HiMoe VLA, it's hierarchical mixture of experts over here. So basically there are different embodiments, and instead of training one single model for all kinds of embodiments, you have an ensemble of that. And then you mix them. For the task, for the embodiment, etc., you have different kind of models. But you share something between them. For example, you can share a KV cache for transformer, okay? Something that you take from the VLA as well. And finally, and in my opinion, that's exactly the frontier where we are now, that's world models, right? That's what Dmitry explained to you for Cosmos and Omniverse and all that stuff. So world models have superpowers. They can turn words into worlds. So basically you can prompt it to generate or manipulate data, right? And have like complete environments just from the prompt. So they can also help you dream. Not you, but like behavioral models can dream. So basically it can predict the outcomes of the actions within the control loop, right? That's a dreaming capability, right? How the environment will change under applied actions. And finally, world models can help to guide having like a dual system. You have like a flow of actions from your model, but then you can regularize that. So you can, incline it towards certain targets or sub-goals. So and here's an example of this control world, right? So they do zero-shot they have world model in the middle to dream, right? And while it's dreaming, from zero shot, that increases the success rate almost 2.5 times, right? So that's the improvement that you can see. Okay. And then a recent release from Physical Intelligence, that's also like one of the, in my opinion, leading groups or leading companies working in the field, is Pi07, is a recent one that's called a steerable model. That's an example of a dual system. When you have some suboptimal demonstrations, some of them are bad, human demonstrations. And then you use that, you learn from that, and then you optimize from this trash, in creating trash into treasure. So, and they also show that probably this is a new direction. Instead of collecting a lot of positive examples from human demonstrations, collect whatever examples you have, good ones, bad ones. Maybe bad examples are even, better than good ones, and you train from that, you improve from them, you give some metadata, and at the end of the day, you have a reliable model. So I think that's it from me. Thank you for your attention. Thank you.
Am I the only one that had a flashback like on the election, and at some point you just lost it and then you don't understand anything after that? I hope I'm the only one, because that was very interesting. And so that was about AI in general, AI fundamentals and so on. Now let's speak about LLMs. So our next guest is Bulat Huseinov. He is my colleague from Yandex. He works at AliceAI. Who doesn't know, AliceAI is Yandex alternative for GPT, Claude, and so on and so on. So it's not only a speaking station, but it's full AI. So Bulat will talk about LLM metrics. He works as a data science team lead at AliceAI. Please welcome Bulat.
Thanks. I want to share 3 iterations of reward design our team went through and what each one taught us. Most RLHF papers focus on algorithms like PPO, DPO, GRPO, reward model architectures. Less is written about something that, in our experience, decides whether the system works in production. How you design the reward signal itself. Quick framing. The model isn't learning to be good in some abstract sense. It's learning to maximize one number. Everything else, guidelines, intentions, product specs, only matters if it shapes that number. The reward is a spec, but it's written in data, but not in code. Like any spec, it can be wrong in ways that aren't obvious. 4 properties we want from metric. First one is stability under shifting priorities. Then interpretability, so we can debug. Unbiasedness, so it measures what it claims. And validity on the distribution that the RL model actually produces. The last one is the hardest, and I'll come back to it later. We started where the most teams start. One composite reward. Careful guidelines with a strict priority order, safety, then factuality, then helpfulness with these sub-aspects, then text quality. Raters rank pairs by this hierarchy. We train a classifier, RL optimizes it. And it worked in a narrow sense. Benchmarks approved, training curves look clean, problems only became visible when we actually look into the data the model outputs. What we saw: longer outputs, more hedging, fewer concrete claims. The mechanism is simple in hindsight. Factuality outranks helpfulness. A concrete claim can be wrong, which lowers factuality. A vague claim can be wrong. So under a strict priority order, the vague answer wins whenever the concrete has any risk. The bigger issue is the right trade-off depends on the query. Some questions need strict factual caution, other needs a real answer. Global priority order can't tell this apart. The structural lesson, and I think it's generalizes, is that the guidelines weren't the problem. The guidelines were fine. The problem is that we put the trade-off into one fixed ordering. This is the assumption we had to drop. The redesign separates two things that iteration one mixed together: the product metric and underlying signals. The metric is overall response quality. The signals are narrow measurements like helpfulness, factuality, formatting, and so on. Each has its own labeling task and its own reward model. The training reward is a linear combination of them. The shift in iteration one, the trade-off was fixed globally in the rubric. Now it's decided per case. Some raters, same raters, very different specification. Trade-offs from global to contextual. Practical benefits. Priority changes become reweighting, not relabeling. New aspects can be added without touching existing labels. Different subteams can improve different aspects in parallel. One pitfall worth flagging because it generalizes. If your candidate model already trades helpfulness for factuality and you sample pairs uniformly, most pairs go the same way on both axes. The reward you call helpfulness actually learns helpfulness minus factuality. Raters are doing exactly what you asked. The problem is upstream in pair construction. A useful check for aspects you think are independent. Pairs should agree on direction about the half time. If they don't, you have a sampling bias. Iteration 2 worked. Aspects were balanced, the balancer did its job, metrics improved. We thought we were done with the architecture. Then a new failure showed up, but this one wasn't at the system level. The framework kept working, the problem was inside one specific aspect, helpfulness. When we originally designed it, we collected reference examples of good, helpful answers. Those references were biased towards a specific shape, long, fact-rich, structured with lists and headers. The model learned the shape and applied it to every query. Simple questions got elaborate multi-paragraph responses. The helpfulness score went up, but the user experience got worse. The aspect was still measuring something real. It just wasn't measuring whether the answer fit the user's task. It's measuring whether the answer matched a certain form. The hard part, this isn't visible in benchmarks, and it wasn't visible in side-by-side either. Because side-by-side was trained on the same idea of helpfulness. Evaluation and reward had the same blind spot. The redesign is something we're working on now. No final result, but I can describe the direction of our work. The question raters answer changes. Not, is this generally helpful, but is this the right answer for this query? Concrete criteria is the link right? Does it stay on topic? Does it avoid adding content the user didn't ask for? The shift is from implicit norms, reference answers raters had to internalize, but to explicit criteria. The broader point is this isn't one-off fix. Any well-designed aspects will, with enough optimization pressure, be satisfied too literally. When it happens, the aspect needs rethinking. This is a recurring cycle, not a phase you just finish. To summarize, any well-designed reward signal degrades once the model can optimize it well. Plan the next version before your current one fails. Separate the product metric from the underlying signals. Otherwise, the system is hard fixed where you need it flexible. Trade-offs are contextual, not global. Putting them in fixed hierarchy begs in a wrong answer, as we see on the previous slides. Pair construction can bias a reward in ways that carefully labeling won't catch. Some problems worth flagging. First, offline reward quality doesn't predict in-RL reward quality, and the distribution shifts isn't solved in any general way, I know. Second, the form versus fit failure I described previous, where an aspect satisfies its definition but drifts from its meaning. It's hard to detect with the same evaluation that produces the reward. After my presentation, I'd be interested in any thoughts on these questions. Thanks.
Did you notice that in Matrix 25 years ago there was agents and they were fighting humans? Is that normal that we have agents now that is AI part of AI? I don't know. So, okay, what we will do next? The next part will be the panel discussion that we will have, I think in 5 minutes, yes, something like that. So, the panel discussion will be with our speakers, and the host for the discussion will be Rand Khachitryan, who is director of YerevaNN, which is ML research group, and he is the lead of that group. So, at Yerevan State University, of course. So, at the panel discussion, actually, I don't know what they will discuss, but I hope something interesting. And since you listened to all that, you all now know AI and everything about that, so I hope you will understand everything. So, and after the panel discussion, we will have also award ceremony, so keep it up, be here, stay here, and listen for the panel discussion, prepare your questions. Okay, so where is Hrant? Okay, welcome, Hrant.
Hello, everyone. Our panelists are our speakers. So Dmitry, Bulat, and Sergey, please join me. So, as you have seen during the lectures, here we have Bulat, who works on text, basically, right? So AliceAI is mostly text-based. And then all others here are more on the physical side of the thing. So Sergey is from like traditional control theory to modern AI. Zima is on simulation side, Omniverse, and he has shown a lot of cool stuff that NVIDIA is doing. And I'm also leading a research group that is trying to build physical AI models. So we build a perception layer. We want to understand what type of sensory input we can give to AI models. And then we also try to do high-level control, which is like, how do you replace a human operator of a robot, right? I think everyone agrees that the text side of the AI research is much more advanced now, right? So when we're talking about digital interactions, when we're working with text, what Bulat was training about all these very complicated rewards and stuff, it's like a few years ahead of what we do for robots, right? So there are things that we can learn from them. And I think the first question that I want to ask is a little bit provocative. So Sergey mentioned that there are laws of physics that are important for a robotic AI or physical AI to know about, right? And maybe we have to inject this knowledge to our AI systems by these techniques that we call inductive bias. And I think many years ago, the same idea was for text-based AI models, right? So we said that just like laws of physics, we have laws in language. We have grammar, we have, I don't know, a lot of the things that linguists know. And most of the language-related research in AI was based around that. We were trying, like, I remember when I was just starting to do AI research, we were doing a semantic parsing of sentences, right? And what Bulat showed us today, there was no grammar, right? Like, there is no human-injected grammar. But there is some reward design problem, for example. So, Bulat, let me start from you. What do you think? Like, what happened to this laws of physics for language? Can we say that we never really needed it to make AIs work?
That's a difficult question, you know. For us, grammar of the language and the rules, language rules, just like formatting reward. But it don't describe the answer itself, the model output. So we need to design some more complicated rewards, functions, evaluations to just have the good answers after our training.
So this linguistics disappeared from LLM research in a way, right?
Yep.
So, Sergey, why do you think physical laws are still important if the example with LLMs showed that we don't need to inject these laws?
Well, first of all, we have multiple languages and different grammar. We are fine with that. The problem is that I think the major difference is that we never used language as a source of knowledge. Language is only the way to kind of transmit it.
Express.
Yeah. While when we talk about physics development, you know, that's a normal process. You observe, you generalize, and then you induce some general concept or method. So, and that's generating knowledge. So that's not only transmitting. So for now, we're still at the observation stage mostly. So we just see some, you know, evidence, and we train something that somehow encodes the evidence. But we still don't have multi-billion parameters model that can do something like F equals MA or E equals MC squared. Right? That's how many bits of data you need over there, how many bits of data you need to store all the weights of this, you know, large model. So that means, like, okay, we're only scratching the surface, basically. So, and as I said, so in my opinion, that's just a guardrail. So the rule, the grammar is just a guardrail to generalize, basically. So, and it turns out that we have multiple languages, but we have a single language of mathematics, a single language of physics, and that's it. And we all agree on that. So I think that's also quite a big difference.
So to clarify, you mean that if a model should learn F equals M times A, it might need a lot more data than we will ever have, and it's better to induce it? Is that what you're saying?
Yeah, I'm just saying that we are happy to have this knowledge already. At least it matches our representations. Why not to use that, right? Why ask models to rediscover everything from scratch? Right? So I think that's quite intuitive. So for the language structure, that's like an artificial structure. We created that. While for the physics, that's something that we discovered, that exists like irrespective of ourselves.
I see. Tim, what do you think about this?
So can you restate the question again?
Yeah, so in language modeling, our experience of the past 10 years showed that every inductive bias that comes from linguistics research is not really needed anymore because LLMs learned to work with language without this. But for physics AI, we still believe that injecting the laws of physics that we know from physics textbooks is still useful. Do you think they will be useful, or it will grow in a direction just like text-based models went, and we will just discard all the physics knowledge and the models will learn everything by themselves?
Great, thank you. So my thinking about this is that it's almost inevitable that it will just discover all the needed laws by itself, given the large enough data set. However, it there's nothing bad in using what we know already, right? To just accelerate to that point where it will discover all these laws. And the other point I wanted to add is that it doesn't have to be precise, in my opinion. Like, I mean, ANSYS level precise physics for majority of AI, embodied physical AI applications. It's okay for even simple applications like grabbing a box or, I don't know, like something very basic, right? It might be okay to use a game-style physics engine, simply because the sim-to-real gap will be still there for a long time, and the robot will have to fine-tune in real world, and we're just getting first 80% as fast as we can, and it doesn't have to be like, you know, absolutely precise. That's just my view, but...
I see.
If I may add?
Sure.
Yeah, I was just thinking, you know, so Yandex core business is search, right? So I already use some, you know, search analogy over here. So, and I think that guardrails like physics laws and all these considerations are more important for the embodied AI is because the search space is also much bigger. The space that we need to discover, dimensionality of this space is much bigger. So a simple example, how many letters are in alphabet? So depending on the language, but that's like quite a finite number. How many numbers are from 0 to 1? Infinite. So, and all these, like if you have like 6 senses, right, that's already not a single one. That's much more dimensions. And it's continual search space. So, and it can be quite sensitive. You change, you know, the 4th digit after the comma, and the result will change, right? So, in language, grammar is, you know, a fixed number of rules, and you work with fixed number of symbols, and that's it. While in embodied AI, you work with, you know, huge search spaces. So, having good guardrails to navigate these spaces is also of more importance, I think.
I see. So if something changes, if you change a number after the 4th digit in the comma, it means that your system should be granular enough in a way to be able to capture that. And a lot of the AI developments now are going into the direction that Zima said, right? We go from FP32 to FP16 to FP8, and at some point we won't be able to even see this. I see. Okay, so another topic that is recurring is where we get the data, right? And all of us talked about simulation data, simulations and synthetic data. And again, this is probably something where we can learn a little bit from text. And I want to ask Bulat about his experience of using synthetic data in text, because there are, I don't know how you do it, Yandex, but there are rumors that, for example, in Gemini pre-training, there is a lot of synthetic data. So both in pre-training and post-training, what's your experience of the impact of synthetic data?
I can say only for post-training, nothing about pre-training. Synthetic data is really useful for just formatting task. Formatting, like how to solve the equations, how to write the right essay, and so on. So synthetic data is cool for just making data sets larger, but the original task is just from real data. You should take it from real data.
Which is a very bad news for the rest of us, right?
No, I think that's what Bulat is saying is, for me, it's quite obvious. I mean, there are even things like data poisoning and everything. So probably we should understand better what information is, right? Information is something that reduced uncertainty. Like reduced entropy. Sorry for being like, you know, professor, but yeah, that's something that reduces uncertainty. We have streams of data which are not information. It just multiplies uncertainty. And when you augment text with, you know, just having another text which brings no better understanding of the, you know, of the structure of the knowledge that you try to convey. You don't provide any information for training, you just provide data. That's it. So that's not much you can learn from that. And by the way, for physical world, 2016, I've attended like an IRAS. It's one of the biggest conferences in robotics as well. And there was Jill Pratt, is the guy who is heading Toyota Research Institute for now. And he delivered his plenary on AI-based simulation for autonomous driving, by the way. And he said, like, if we just reproduce normal driving conditions, we'll need forever to train and validate. Right? So how many hours of driving you need to collect to prove that an autopilot that you want to deploy is above the margin that allows it, to deploy? That's, your competitors will release the new generation until you're still validating, right? Or your team, the entire training team is just, sitting and waiting for several months, waiting for the validation until they implement some new stuff. We need, Bulat has mentioned that you have pre-train and then you have fine-tune. I call it specialization, right? So I think that's really important that you find the right corner cases. Something that really, brings the model to the limits to really, check its performance. And the same for training. You better have less good data than just more data. I think that's, in my opinion, what Bulat is saying is quite obvious, and that extrapolates from text to whatever modality, I believe.
And what Dima showed on these self-driving simulations, that's exactly this corner case that Sergey mentioned, right? This tree falling on the... how do you see the value of simulated data? Because in robotics, we don't have the luxury of annotating, like all these companies, I'm sure, including Yandex, spend a lot of money actually on annotators to fix this data, but like in robotics, like you can't even really do that, right? So you...
Right, yeah, absolutely. I wanted to maybe comment, even though I'm hugely out of my league. I'm not an expert here, but just wanted to add a comment on adding synthetic data for LLMs specifically. For the most part, I agree with Sergey. However, I can imagine approaches similar to Cosmos done for text. It's just that historically it hasn't been needed to do this because we have so much text data already available. However, I can still imagine certain cases where, as an example, you train multilingual model and you have another model on the side that is very good at translating to different languages, and you just want to improve certain, you simply miss some knowledge in some languages, right? Like some China-specific problem space is missing in Russian language corpus of text, right? But still you want the model to be able to answer this China-specific problem space in Russian, and so you can improve this data set by using this side model. This is a very simple case, but I can build on this and like make it multi-problem space or somehow maybe one other thing I was wondering if with the AI boom happening some years ago is that in the academia there's all these like spaces of and they're very well self-connected, right? Like people working on biology normally, for the most part, talk with people working also in biology, and then the same happens in each space of academia. But the magic, we've seen it time and time again, sometimes happen on the connection between these spaces, like biology and informatics, or you know, some other good combination. And the AI could very well try to apply some approaches from one space to another, right? Going back to self-driving examples. Yeah, I think it's very obvious that given enough compute, and that's a big stake, we can produce good enough data sets for robots and for cars. What happened with, I sometimes wonder, could something similar to what happened to Tesla happen to robotics in general or not? What I mean here is the stake that Tesla took was that they will get their feedback from real world, from their fleet of cars, right? If someone disables the autopilot or, God forbid, it gets crashed or whatever, all the video footage from all the sensors gets sent back to the Tesla headquarters and used for quality assessment and retraining, etc. And that's a very good and robust approach because it's grounded in reality as much as it could be. However, I'm not sure if the same approach could be used for just general humanoid robots or simpler robots, just some hands grabbing something in Amazon warehouse. I'm not sure. I could imagine Yandex or some similar company releasing a humanoid robot just for fun, and cheap enough for people enthusiasts at first to buy it, and then they would collect the data set at home. Maybe, I don't know. There are many questionable like challenges there, right? But I could foresee in principle how this could follow the same Tesla way, but I tend to believe in simulated approach more.
Yeah, please. Just over here. By the way, that's already happening, right? The most common approach for now to train these kind of models for robots is just demonstrations. Like you collect demonstrations. It's like teleoperation, like robot in the loop, robot out. So there's watching. So there are some sewing factories in India where workers have like egocentric view cameras and they do some sewing and they just collect the data, and they use it for training.
It's not really demonstration, right? If you teleoperate, it's more like supervision directly.
There are different. No. I mean, what they do, they just do the normal sewing. Yeah. Probably otherwise they will be fired. So like you are fired or just wear an egocentric camera and will be fired a couple of years later when we bring a robot that can do the same stuff. You have a choice. So, but that's crowdsourcing is already happening. I'm not saying that this is the best approach. So as I said, in my opinion, just having more and more data is probably not the just normal data is not the best way. But this is something that works, and that works now, right? And then you have a company, you need to deliver something, and you need to show some progress to your investors. So even though it's not the best way, at least it's something that is working. So, and they're just scaling now. So they just collect more and more data and, have it in the loop. But I think at the same time, for example, the P0.7, the one that I mentioned from physical intelligence, they even claimed that having expert policies, RL policies, instead of multiple demonstrations, works better than have many data from demonstrations. So you learn from an expert policy and then you generalize. So you combine multiple RL policies into a single big model.
And where do you get the expert policy?
You train it in a simulator, and then you can scale. So in the physical domain, it's hard to scale. It's real time. While in Omniverse, for example, you can scale like 100 times. If you have enough compute, you can run all the stuff. You can train RL online, right, and train expert policy in simulation environment completely, and then deploy it and distill all the models into a single big one. That's also what is happening now, and I think that's an interesting path, and I think that can even work better than the current learning from demonstration. The other story is that another big business I think for Yandex is like labeling the data and the crowdsourced data, and that's definitely expanding the business to new modalities, right? And then you should think about it. Before you had human for labeling, now is not enough. Like how you can label tactile data? That's an interesting question.
I see. Thank you. Bulat, one more difficult question for you. So Dima mentioned that there are cases when you want your model to answer in Russian about something in the Chinese context, right? So for maybe for something that you have data in Chinese, but you will probably never have data in Russian, but then you want your AI to answer about this in any language you ask. And I think we already see that in ChatGPT style products, because when I am pushing my students to ask difficult mathematics question, like university level questions to ChatGPT or Gemini or even the big Chinese models, I see that they answer a lot of good mathematics questions that I'm sure do not exist in any Armenian literature. So apparently these models learn general knowledge and then express this knowledge in every language. Have you looked into that in AliceAI? Like, how does it happen, or when it happens, when it doesn't? Any experience you had?
I think it's all about generalization, you know. So as we discussed earlier, your first question was about language rules. I think that language rules is about how to express the thinking process or just the thought the model wants to express. That's why I think you need some data for fine-tuning on different languages and different grammars, but the thing that the model can express what you ask.
So in your experience, when you do RL or SFT, I mean, mostly RL probably, you do it in not every language that Alisa supports, right?
For now, Alisa supports Russian, English, or... So,
okay,
but we try to train it on different languages. So Alisa can speak any language from pre-train, so...
And when you do SFT or RL in Russian,
yeah.
Do you see that it improves the same skills in other languages, or you don't measure?
Yeah, it improves in English, for sure.
See.
Yeah.
Yeah, this is crazy. I still don't know how it works. Dim, one question for you. So, and Sergey might help as well. So I'm a little bit confused about distinction between regular video generation models like Veo, or what was the OpenAI's version, Sora, which is died a few months ago, and Cosmos, the world models that you mentioned, and DeepMind's Genie model, which is playing. Like, what is the structural differences between these three? Are they essentially the same video generators, or there are core differences?
I think, again, I'm out of my league, but I'll do my best.
Thank you.
think all of them are autoregressive or the diffusional models as like the part that actually generates pixels. However, the loss function is hugely different, right? So for Genie versus Veo, at least as far as I'm aware, Genie is also some sort of word model, whereas Veo is not. Veo is like, give me a nice 15-second video, and nice being very subjective here, probably with like some prepared data set curated to actually look nice, right? For like Instagram or TikTok, I don't know. Genie seems to be closer to what Cosmos is doing. However, I don't think Genie is grounded in physics. And as far as I am aware, Cosmos is. And there are like mathematical approaches to make sure it is grounded in physics. So there are things like physics aware neural networks, or PIN, it's called, I believe, PINs, physics informed, thank you, Sergey, neural networks. So that is definitely was part of the training of the Cosmos model, whereas for Genie, I don't think this was the case. If I'm not mistaken, with Genie, you can generate some, miracle worlds with some rules, right? Like game-like worlds where physics is not necessarily a constraint.
Mm-hmm. And more importantly, Genie allows you to navigate in this world, to act, right?
Yeah.
So you did a few very good examples of systematically structuring what's happening, Sergey. Can you do that for this world model part as well?
We'll be happy to. So let me give you like a user experience, because we use a lot of NVIDIA tools and resources in our developments as well. So, since I started talking about Yandex businesses, even though it's not my business, but anyway, so that's another big business for Yandex, I think, is entertainment, right? So, and imagine that you have a model that creates you like a movie versus a model that creates you a computer game. And by the way, when these world models have been released, you know what happened at the stock market? Game developers' stocks dropped, because that's a huge game changer, right? So imagine that everyone can design a game from a prompt. I mean, you don't need a studio, you don't need a huge compute. You just So in my opinion, so we use a lot of ISAC. We use ISAC lab, and that exists for many years already. That's like a simulator with a physics engine. And in my opinion, Omniverse and Cosmos in particular is something that takes both video generation from prompts and a physics engine and brings it in a single package. So that's very important. So there is like an underlying physics behind what you're doing, and you learn from that. You cannot learn from the video, because you always, if you talk about RL, you have state action pairs. You need state action pairs. And the causality between actions and consequences of actions should be valid, right? So if you start, flapping wings, you should go up, or you should navigate the stream, etc., etc. And by the way, that's pain in the ass for simulators to work with like flows and fluids and everything. ISAC is a powerful tool. Try to work with liquid over there. That's a nightmare. I mean, and if you can do something like that with a new generation of models, that's a holy grail of what you can do, and you finally close the loop. So before, of course, we had some, URDF, MGCF, all these configuration files for simulator, but it's handcrafted. At first you need to configure. Now imagine that you can do everything automatically, right? You just, you give the context and then it goes. Right? The simulation goes, you define corner cases, you discover it on the way. That's like AutoML in the simulation. So I think that's very powerful.
And do you know any open source things that are close to Genie level of game generation, or we are still, as an open source community, a little bit behind?
I think we're a little bit behind. Also because it requires enormous amount of compute to build. An open source probably can, but maybe NVIDIA will release something. NVIDIA does a lot of open source stuff for now, and just killing all the competitors who are trying to to make money out of that.
Okay, thank you. So Sergey mentioned that now game development company stocks are going down because it's possible that after some time we might be able to develop our own games by just prompting inside Gemini or something. And this question is happening at every industry, right? So it's possible that we don't need game developers, then we don't need website developers, then we don't need other types of software engineers. And then there is a question on what we should actually teach to the next generation of students if all of this is going to happen inside. And I think we don't have much time, but we can directly transition to AliceAI's presentation, which is right about that question. So what we should learn in the age of AI. So thank you very much, guys, for this discussion.
So our next speaker is Alexey Tostikov, which is head of Yandex School of Data Science, and he will talk about the how to teach and how to learn. So welcome, Alexey.
Thank you very much. Thank you, dear guests, dear friends, for joining our meeting today, our meetup. It's a great pleasure to see you here and to speak about learning and teaching. Actually, I will not say more about what we should teach and what we should learn nowadays. You have heard a lot of information about physical AI as a new domain, about text domain, and a little bit about AI in general. But my speech is more about, is a little bit more philosophic, I think, or a little bit more humanic. And I want to tell you what in my mind, in my head, almost every day is what's happening around of us. I'm Alexey Tolstikov. I'm head of Yandex School of Data Analysis. It's a master level program in AI and infrastructure for AI systems. And we work a lot with university. It's around 1,000 students in our programs every year. And today, I will not steal a lot of your time. I think that we can discuss some ideas in network part, and I think I will more ask questions than provide the answers for them, just because I think that nowadays we have to ask these questions ourselves, just because we don't know what is world of future, in near future around of us, where robots and physical AI systems will do almost all job, I think. In my imagined world of near future is a real true. So in the age of AI, I want to ask you a question, not about how to find the answer, but answer yourself. Who is a thinker inside of you? Can you ask you some specific questions and find answer from your own position? And about position is one part for our discussion today. I want to split my speech in 5 parts. I will start from something what is actually changing right now. Then we'll continue with some patterns of behavior, of our behavior with systems and actually with other humans sometimes. When we usually ask a question and expect the answer, or ask someone to do something and just expect the result of this act, of this action. And some words about subjectivity and what is forces around our own subjectivity. And a little bit about the role of teacher, the role of learner, and how I project it into my own life. And a little bit conclusion with self-reflection, as I like to do. So what is actually changing? And one part I want to discuss. Usually we can hear that there is common opinion that when you ask AI system like ChatGPT, Gemini, AliceAI, you get state-of-the-art result as the answer of system. It's time only seconds to find this kind of result. And what changed between several years ago, 5 years or maybe 10 years ago, when we trying to find answer ourselves, and nowadays with AI systems. Several years ago, we have to find some answer. Nowadays, we have to try correct question to ask the system. If several years ago, to find great, deep answer, you should be mastering this domain. But nowadays, AI systems is mastering almost everywhere, and we ask only this system to answer me as your professor in physical AI, or answer me as you a teacher of elementary math. I'm not so deep in this field, and system answer us in that style, in that depth of knowledge that we can understand, of course. Yesterday, we have to consume some knowledge and to be a little bit great, a little bit higher as professional. Nowadays, we have to know what real position I can stay by. And if I am quite good, for example, in medicine, I can ask some system. I am 10 years work at this hospital, for example. Tell me the interesting things about some kind of epidemic or so. And yesterday, we have to choose one framework that was suggested by your leader at work or some leader that we can hear or read in internet. Nowadays, these frameworks continuously change it. We have to apply new and new things and trying to know how to work with AI system of next generation, which actually produce almost every month or sometimes even every week if we work with several companies, several vendors of AI system. So my answer to the question on the left part of this slide is not actually one can get state-of-the-art result for his or her question. To get state-of-the-art result, you have to know what is actually state-of-the-art result. You have to understand it, and without it, it's just some words that you can read, but not get actually the part of human knowledge that is behind AI system. Right now, it's much more about human knowledge, but as you know, several AI systems produce new knowledge, new theorems, for example, or new forms of engineering nowadays. So, my question to you, to all audience, please raise hand. Who tried a little, for example, last week to solve some problem without browser, without AI system, without even computer, just get pen or pencil, just get a sheet of paper and trying to do some yourself. I have tried, and I think almost half of audience have tried it, and I think it's really hard nowadays. Just because if you solve so easy question, it's great. I succeed. But if you're trying to solve a little bit harder question, almost all of us trying to say yourself, okay, I do my best, I did my best, I will continue with some assistant. So, some words about what's changing. Some words what patterns of our work nowadays. I trying to split into lists. One of them is give me the answer. We usually ask questions to systems. And actually such kind of action do not provide knowledge for us. Just because when you receive the answer and you almost believe the correctness of this answer, you do not find exactly incorrect answers. And it's very hard to find the mistakes in these answers and how to make a critical decision with new information for you. And if we will lost the numerous ways to that is actually finishing deadlock, we will lost the way how to find actual pass to correct answers. And I think it's a big trouble of future for us if we will not can find correct way to find the correct results, or best or new results, better than yesterday. And other kind of thing or action is just do it, as we usually ask, for example, nowadays agent systems. And we try to say, for example, for AliceAI, just call me a taxi, or just make me some decision, or how to do something. I lost my own experience how to make it. And if I lost experience of making, I actually cannot reflect. I lost reflection of myself mistakes in action as well, not only as in thinking before. And some summary of these two ways of our action is the next one. I think that almost of this audience are quite smart, even smarter than me, of course. And when we are enough good at some action, we are so easy can justify these patterns for yourself. You can say, of course, I can do it myself, but I save a lot of time when I ask AI system to solve some problem, or I don't know, to write some letter for my friends, or to validate my short idea, my first think of idea, and to find the correct, is it correct of all in all or not. After that, I want to say for all of you that actually subjectivity is my own idea why I do something is under pressure nowadays. And I want to try to prove it with considering these three forces that are actually behind my idea, behind my statement. When we work with AI systems, it's usually so fluent answers produced. It always looks like correct, it's always so smooth, and it's hard to find things that is actually provocate you with do or think in other way. Otherwise, we are working in some community, we are living in some community, and almost that we think and almost that we do is actually the echo of community voice. Just because it's, I think, human nature to hear what is around of you and trying to be not usually provocative and trying to prove your own position, your own ideas. To be in the stream with community is actually quite okay. And I want to project it with AI system as well. AI systems nowadays, not in the future with physical AI, but nowadays is learned by numerous texts, videos from humans. And when you ask some for AI system, it answers by the voice, by the thoughts of other peoples that is inside of data AI system actually learned. And the third force is about benchmarking. It's about trying to measure everything around of us. We are trying to measure our work, how many tickets we have finished yesterday or last week. We are trying to measure our, I see, for example, posts in social networks, how many readers, how many subscribers in my channel, and so on. And if you measure everything around of you, it's a big change you should expect. That actually the system can start to measure you itself. When we work with AI systems, they collect our data, our questions, our queries, and becoming much more confident with your questions and not trying to ask you bigger answers, providing you bigger questions or problems in your life. And some summary for this part of our discussion as well. How do you keep your own voice? How we can raise our own voice and produce your own position? And one more about teaching, one more about teacher as a role in our life. When almost any question human can answer worse than AI system. Any specific question, maybe not any specific question, but in general, if you're trying to ask 1,000 questions to AI system will answer in more percentage for these queries better than any your friend or your relative or even your head at job. But some specific questions, I think that human can answer a little bit better and deeper. How to find such questions and how to find such humans who can answer in this way. So I think that near future is living in the world with AI teacher and human teacher as well. And some questions we have to ask to systems and ask to make some work and some job instead of yourself. But human still can tell you what is actually was not written down. The experience of negative examples is still not the part of learning AI systems. It's not new idea from me. It's an idea that actually you can hear, maybe not all around, but in most places, that negative experience is very important part of our life. And AI system is not so good at this way. And finally, my own position, your own position, understanding what you know and what you want to do, it's not transferred from someone. You should find it in yourself and grow it as possible as you can. And wrong decisions, mistakes, is a great part of yourself. So the next idea is you're already a teacher. And there are so many people around of you who are actually a teacher for you. And nowadays, we are living in time when teaching and learning it's a spiral way of living. I think maybe such kind of conclusion is very specific for me. And you should share your experience. When you do a code review at job, actually you teach someone and you share your knowledge. And of course, giving and receiving honest feedback is a great part of our life. As about me, I don't like very smooth feedback. That it was quite okay, it was quite good speech from you here at stage. If you have strong opinion, please give me it. It was not so good just because I expect something another. It was very good just because you asked such questions that is very important for me, and actually I ask it inside of me every week, and now I want to discuss something about these ideas. And I want to summarize, as in previous chapters of this speech, with 2 sentences. I think that one conversation can redirect someone's thinking. Only one conversation. It can be a point of bifurcation. And the continuous of this idea is we will probably don't know which conversation is. And another part of this final statement is you cannot know who this person, whose life or way of thinking will change. It's not transferred one-to-one nowadays, but a week later, a year later, or maybe even 5 or 10 years later, someone will tell you that discussion maybe on 31st of May here in YerevaNN Hall was changed some in my life. Actually not for me, for any speakers here or any in audience during the network discussion, such ideas can rise. And we have started with a question, what is the point of learning anymore? Why we should learn? My self-reflection for this question here on slide and here in my speech, I like teach. I like speak with other humans, with other persons. I really like when the performance of my students is better than mine one. It's some point of happiness for me. And I think that as many such students will be, as I will be happy. So, the only final idea. Try to find person you are trying to learn from. Tell him or her that you are trying to reconstruct point of view of this person, and you are trying to learn from it. And of course, don't stop and teach another people. Teach your children, teach your friends, share your experience with them. I'm trying to share my experience of learning in my channel. It's not so many posts from me here, but I think that when I trying to point some ideas of or some actions of my life, it's very important to write it down and share with another. I like when someone answer me in support of this idea or discuss that there is another point of view. So thank you for this 15 minutes. I think I don't know how many time I have told to you. And I hope that we will network and discuss some ideas, some questions I have raised right now. And we will go to next stage of our program today. Okay, thank you.
Yeah, yeah. Please stay here, Alexei. I think you will be needed here because The next part of our talk is we're now proceeding to Yandex Coding and Math Contest, award ceremony for that. We also invite Dmitry Kozyrev here. Please welcome Dmitry. So I think the next part is to Dmitry.
Thank you. Good afternoon, everyone. Baravzes. My name is Dima. I am academic supervisor of the mathematics track at Yandex School of Data Analysis. And I have the honor and pleasure to announce the results of the Yandex Coding and Math Contest, a competition that was jointly organized by Yandex Armenia and Yandex School of Data Analysis. First thing first, a few words about the competition itself. This is a two-round competition in mathematics and programming. The first part of it, the first round was held online, and the second one in the in-person format, right here in this very hall 2 days ago. We have received more than 450 applications for the competition from both students and IT specialists as well. Over the two rounds, the participants solved problems in algebra, linear algebra, probability theory, algorithms, and mathematical analysis. And 25 of them managed to reach the finals, the final round. And today we will announce the 5 winners. One more important thing to note, the finalists of the CMC contest will have the opportunity to get reviewed for internships at Yandex. And on top of that, they will also get a chance to fast track to the Yandex School of Data Analysis, which, as Alexei already told, is a master level leading educational program in the field of machine learning, data analysis, and big data infrastructure. So the 5 winners from 2 major Armenian universities, the YerevaNN State University and the American University of Armenia. Well, let's move on to announcing the names of these winners. The first one, Petrosyan Hamlet. My congratulations.
Congratulations. Please stay here. We'll take common photo.
Congratulations. Next one is Robert Kacharyan. Is Robert here? Yeah, great. Congratulations. Tsovak Yagaryan. Vagan Bagdasaryan. And Hamlet Mikhailyan. Congratulations.